Now, one thing about number 7 is this circle that I drew is not going to represent the orbit of, in this problem it says a coin is placed on a record. I don't want this to represent the orbit of the coin about the center of the record. I want this to actually represent the record. So that's a record. So in the 30 centimeters that's given in the problem isn't really, I'm not going to use that number to solve this, but what it tells me is that if the radius of this is 30 centimeters, if the diameter is 30 centimeters, then the radius is 15. And so if the radius is 15 and the coin can be put on the record no more than 10 centimeters away, no more than 10 centimeters away, then I know it's still on the record because I know the size of the record. Like I can't have it put 18, like this number right here can't be 18 centimeters because 18 centimeters wouldn't even be on the record. All right, so it has to be on the record. So the way I'm going to do this for a picture is I'm going to put the coin on the record. So from there to there is 15 centimeters, and from here to there is 10 centimeters. And what that means is that as long as I don't push this too far out, it will move with the record. It will move with the record. Think about it. If I had the coin right in the middle, there's not even a thread of it slipping because it's just going to rotate. It's just going to go around the circle. It's not going to rotate. If I have it a little bit away from the center, it's going to move through a small circle. The smaller the circle, the smaller the velocity. So it's easier to move without slipping at a low velocity. But as I move further and further away, at some point, I'm going to get to the point that if I go any further, I'm not going to have enough friction between the coin and the record, and it's going to slide off the record. So we know how far, at least for part A, we know how far the coin has to be based on the coefficient of friction so it will not slip. It can go up to 10 centimeters. Anything more than 10, and it's going to slip. So I use the 10 as my limit to figure out the coefficient of friction. So my forces, I'm going to still have friction in that direction, which I'll label friction. And I'm going to still have the normal force up and the weight down. Whoops. The normal force up and the weight down. And so I'm going to label that as W, and that is the normal force. So if I'm grading this, I'm looking to see that you have a diagram and you have those things labeled on your diagram. Once I have a diagram, that allows me to now write some descriptive equations. If I sum up my centripetal forces, I'm going to get friction equals, it's either going to equal mv squared over r or mr omega squared. Now in this problem, the unknown is not the radius, it's the coefficient of friction. We know what the radius is going to be, so I'm going to use mv squared over r. And if I sum up my forces in the y direction, it's going to be Fn minus W equals 0. So just like the last problem, I'm going to write Fn equals W and W equals mg, because I'm probably going to want to replace the normal force with mg. So the unknown is mu. So I'm going to, like I did in the last problem, I know that friction equals mu Fn, and I know Fn equals mg, so I have that friction equals mu mg. So I have friction equals mu mg, and I have friction equals mv squared over r. So if both of these, so if friction equals this, and if friction equals that, then I know that mu mg equals mv squared over r, because they represent the same thing. So I'm going to write mu mg equals mv squared over r. And what can I cancel out again? M. And if I'm solving for mu, mu is going to equal v squared divided by rg. I just divide both sides by g to get that. Now, the difference between this problem and the last problem is the last problem, they gave me the v, they gave me the r, and g we always know. In this problem, they're not giving me the v, but they're telling me that the record is going to rotate at 33 RPMs, and we know how far away from the center of the record the coin is. So I can do a conversion. So I'm going to get my v from my angular velocity of 33 RPMs. So 33 RPM means 33 revs per minute. It never means radians per minute. If you see RPM, RPM means revolutions per minute. And I say that because I have people come up to me during the test and they're like, what's RPM? Is it revolutions per minute or radians per minute? Revolutions per minute. So I'm going to extend the line. I'm going to go from revolutions to meters because I want meters per second. And I'm going to go from minutes to seconds. So we have one revolution would be how many meters? What? 2 pi r, right? Because it's going to move through the circumference of the circle. And the formula for the circumference of a circle is 2 pi r. So I have to put in the r. And what should I put in parentheses there? If it's 10 centimeters, what do I need to put in there? 0.1 meters, or 0.10 meters. All right? 0.10 meters because it has to be in meters per second. And then one minute is 60 seconds. So if you solve this, this is going to give you the V. And what does that work out to be? I've had this problem on versions of the test where I don't even give you the part A. Like, you have to do all of this to get part B. Because you can't solve it without knowing the coefficient of friction, and you get it from all this information. Then in part B, I'm going to put the coin at a different place. The record's going to be going at a different speed. So if it goes at a different speed, I can't keep the coin 10 centimeters away from the axis of rotation, or it's going to fly off, because I'm going to be going at a faster angular velocity. So what's the V here? Yep. 0.346. 0.346 meters per second. And so now I can just plug into my formula right here to solve for mu. So mu is going to be V squared over Rg. So I'm going to put in 0.346 meters per second. I'm going to put in 0.10 meters and 9.8 meters per second squared. And that's going to give, what, 0.122? You plug in those numbers, 0.122. So that's your answer for part A. Now for part B, it says how far from the axis can the coin be placed without slipping if it's rotating at 45 RPMs. Well, 45 RPMs is faster than 33 RPMs. So that means if I keep it 10 centimeters away, it's going to fly off the record. So I'm going to have to bring it in a little bit. Well, the unknown is going to be, where do I bring it in? How far do I have to bring it in? So our equations are still going to be the same here, except I don't want to use mv squared over r. If r is the unknown, I have to use mr omega squared. And the reason for that is all of your unknown, which is r in this problem, have to be exposed. They all have to be exposed. And v equals r omega. So if I don't replace V with R omega, then I haven't really isolated R. So the only difference between part A and part B is that I'm going to change this formula to set it equal to mR omega squared. So my new equation, when I sum up my centripetal forces, it's going to be friction equals mR omega squared, because R is going to be the unknown. Well, we now have F equals mR omega squared, and we still have, we still know that friction equals mu Fn. So friction equals mR omega squared, but friction also equals mu mg. So it equals this based on this equation, but remember, friction is mu Fn, and Fn equals W, W equals mg, so I'm just replacing the Fn with mg. Well, if friction equals this, and if friction equals that, then these two are equal. So I'm going to set them equal to each other, and then I'll be almost done with the problem. So I'm going to have mR omega squared equals mu mg. What can I, again, cancel on both sides of the equation? M. And the unknown in this problem is R. So I just need to move the omega squared down there, and I'm going to get R equals mu g over omega squared. And the one thing about this particular formula, like I told you, we're going to have extra radians. Like, I know this answer has to be in meters, but because that's why I try and avoid this, because the radian is like a fake unit. It's a unit that allows me to get from something that's rotating to something that's actually moving through space. So, but this also has to be in what units? What does omega have to be in for units? Anytime you use omega, what radians per second. Okay, so I need to do a conversion because they didn't give me the angular velocity in radians per second. They gave it to me in revolutions per minute. So this has to be converted. So I'm going to convert that. I'm going to take omega, and I'm going to write it as 45 revs per minute and I'm going to convert it from revolutions to radians and from minutes to seconds. 1 minute is 60 seconds, and how many radians in a revolution? 2 pi. So if I solve that, what do I get for my omega? You have to hurry here because I can only go 15 minutes and I'm at 13 and a half minutes. So I've got a minute and a half to finish this problem. 4.71. So now that I know that, I can just come over here and plug in my mu, my g, and my omega squared. And even though this was a part B and the record is going faster, it's not going to change my coefficient of friction. Whatever, how slippery it is, it's still the same thing, whether it's going faster or slower. So I'm going to use my answer from part A, 0.122. Gravity is 9.8 meters per second squared. And I'm going to put in 4.71 radians per second. And I'm just barely going to get this problem in. The answer for the R is 0.0539 meters. So about 5.4 centimeters. So I was at 10 centimeters when it was going at 45. I had to move it almost halfway to keep it from slipping at 30. I mean, at 33, I was going at 10 centimeters. I could move it at 10 centimeters away. Now I need to, I better stop this.